As we start Chapter 10, it's going to be helpful if we remember some things that we did in the beginning of the year. We started off this year with linear equations, and we graphed lines. The very simplest line we could have was the line y equals x, where x is the x-coordinate and y is the y-coordinate of points on the line. When we graphed the line, it looked like what's shown here in red. It had a slope of 1, and its y-intercept was 0. We noticed that this was the simplest equation of a line we could have. We're going to call this a parent function. It's like the very most basic linear function out there. Then we made some changes to that function. When we added the coefficient, that is the number in front of the variable, we put the m in front of the x, and m represented the slope of our line. Different numbers for m made our line have different slopes. A big M meant that the line was very steep, and a little m gave us a line that was more flat. The line still went through the origin, and it was still a straight line, but m changed the slope of the line. Then we added a constant afterwards. We added this plus b, and b was the y-intercept. b took our line and shifted it up and down. It changed the y-intercept. b is where the line crosses the y-axis. If b was a large number, then our line moved up. If b was a smaller or lower number, our line moved down. So m changes the slope of the line, and b changes the location of the line. What we're going to be starting with in Chapter 10 is a different parent function. Instead of y equals x, we're going to start with y equals x squared. If we were to graph a bunch of points that are solutions to the equation y equals x squared, we would see that all of those points together form a shape like this, and we call this shape a parabola. If we add a coefficient in front of the x squared term, it's going to change the steepness of our parabola. So for example, the parabola shown in red here corresponds to an a value of 1, y equals 1 x squared. If we make a bigger than 1, our parabola stretches up and becomes skinnier. It might look like this. If we make a number that's smaller than 1, our parabola flattens out. It's like we took it and sat on it and flattened it out. So this is what a less than 1 might look like. If we took our a and we made it negative, it would actually flip our whole parabola upside down. We can also add a constant after the ax squared term. So we could have an equation that looks like y equals ax squared plus c. And the plus c, in this case, has the same effect on a parabola as the plus b did on the line. So again, here's our parent function, y equals x squared. If c is greater than 0, our parabola shifts up. If c is greater than 0, our parabola shifts up. So if c is 5, our parabola shifts up 5 steps. If c is less than 0, our parabola shifts down. c tells you how many steps up or down you move the whole parabola, keeping its shape constant. What I'd like you to do now is to please pause this presentation for a moment to do a little bit of exploring of how changing a and c will affect the graph of y equals ax squared plus c. If you pause this presentation and go into Moodle, you'll see the link below. This is actually a link from a site that your textbook publisher creates, and what it lets you do is play with a little slider bar that changes the values of a and c, and you can watch the parabola change as you do that. After you've had a minute to play with it, come on back to the presentation. When you're doing your work in section 10.1, the problems are going to ask you to compare the graph of a particular parabola with the graph of y equals x squared. When you compare it, you're going to use the terms vertical stretch to indicate that the parabola got taller and skinnier, vertical shrink to indicate that the parabola got flatter, shift up to indicate that the whole parabola moved up, or shift down. You'll also use the term reflection to indicate that the parabola was turned upside down. Now we need some new vocabulary for this section. The first term we need to define is the vertex. The vertex is like the tip or the nose of the parabola, and it's either going to be the highest point on your parabola or the lowest point. So for example, for this parabola shown in red here, this parabola has a lowest point. So the vertex of this parabola is the bottom of it. This parabola also has a minimum point. It has a bottom point. So the vertex of this parabola is the lowest point on it. The parabola shown in green has a highest point on it. Because it is an upside down parabola, it has a maximum value. So its vertex is going to be at the top of that green arc. The y-intercept for a parabola is the same thing as the y-intercept was for a line. It's the point where the parabola crosses the y-axis. And the coordinate of that y-intercept is 0, c. If your equation has the form y equals ax squared plus c, c is the y-intercept. The axis of symmetry is a vertical line that splits the parabola right down the middle. So just imagine drawing a straight up and down line through the vertex that splits your parabola in half. You're going to be asked to graph quadratic functions in this unit, and you have two choices. The first one is to do it by hand. In this case, you would make an xy table. You would plug in a number for x. You would find out what y has to be to make your equation balance, and then you would plot all of those points. At this point, I would recommend choosing the points -2, -1, 0, 1, and 2. And what points you choose will change as we move on to more complicated equations. So you can make an xy table and plot your points. Another option is this is a great thing to use your graphing calculator for. So you're going to go into the y equals screen in your graphing calculator and enter the equation that you're trying to plot. Then you're going to hit the button that says graph. If you don't see the graph of your equation in there, it may be that the viewing window on your parabola is looking at a part of the coordinate axis that doesn't have any of your graph in it. So you may need to adjust the window so that you can see the parabola you've graphed. So we have this y equals ax squared plus c. What seems to be missing? Well, we notice that there's no bx term in the middle there. When we add that middle term, y equals ax squared plus bx plus c, notice this looks a lot like the equations that we've been factoring in Chapter 9. What that does is it actually shifts the parabola on a diagonal-ish kind of way. So here's what we need to summarize. If a, that coefficient in front of the x squared, is positive, the parabola opens upward. If a is negative, the parabola is opening facing downward. If the absolute value of a is bigger than 1, that is, a is numbers like 2, 3, 10, or -2, -3, -10, then the parabola represents a vertical stretch. It's a skinny parabola. If the absolute value of a is less than 1, that is, a is some fraction, 1/2, 1/3, -1/2, -1/3, the parabola is going to be more flat. It's going to be a vertical shrink. C is the y-intercept of our parabola. The point 0, c is on the parabola. Notice that in the equation above, it doesn't matter what a and b are. If you plug in 0 for x, the equation you get is y equals c. So 0, c is a point on your parabola. And so what does b do? Well, once again, b sort of slides our parabola. If you go back into the animation window that you had before that you had opened before from your textbook site, you can change b and you can watch how your parabola moves as you do that. All right, so again, 0, c is the y-intercept for your parabola. We said that we had the vertical axis, this line that goes straight up and down through the vertex here. This is your axis of symmetry. It's shown as a red dotted line here. The equation of that line, the red dotted line, that's the line x equals negative b over 2a. So take negative b from the equation and divide it by 2 times a. A is on the bottom in that equation. So it's negative b over the quantity 2a. The vertex then, the tip of your parabola, we know its x-coordinate is negative b over 2a because it's on the line x equals negative b over 2a. To find the y-coordinate of that vertex, what we have to do is plug whatever number negative b over 2a is, we have to plug that into our equation for x and see what y comes out to be. Some more vocabulary we need to define are the terms maxima and minima. These are actually plural terms. Maxima is the plural of the word maximum. You know that maximum means the biggest value. So maxima with the a on the end just means the biggest values. Minima is the plural of the word minimum. You know that the word minimum means the smallest. So minima just means the things that are the smallest. Look at the parabola on the left. It has a maximum point. It has a top or a highest point. That parabola has a maximum value. Look at the parabola on the right. That parabola has a minimum value. It has a lowest point. The vertex of a parabola is always either the highest point, that is the maximum value of the function, or the lowest point, the minimum value of the function. Whether it's a maximum or a minimum depends on which way the parabola opens. We're going to look at an example of how we can use what we know about the vertex of a parabola to solve a problem. This example goes with problem number 40 on page 639 in your textbook. In this example, y is a function that tells us the height of a jumping spider in millimeters, and x represents the time since he jumped as measured in seconds. So just a fraction of a second after he's jumped, maybe he's not very high because he's still on his way up. A little while later, he will have reached the highest point that he's at, and then he's going to start falling back down towards the ground. So the question asks, after how many seconds does the spider reach his maximum height, and what is that height? So y represents the spider's height. So I want to know, what is the greatest value I can get for y out of this equation? What number do I have to plug in for x that makes y be the biggest it could possibly be? And then it says, what is that height? Well, that height is going to be whatever that biggest value of y is. In other words, what's the greatest value we can get out of this function? What's the greatest y? And what's the corresponding input, x, that goes with that function? One way we can solve this is to enter this function into our graphing calculator. We'll enter the function y equals negative 4500x squared plus 820x plus 43. So we enter this into our graphing calculator, and we're going to use the maximum selection from the calc menu to find the coordinates of the vertex in this. So if you look at the parabola shown here, that shows you how high the spider is after a certain number of seconds. It's like that parabola traces the spider's flight. And we want to know, for that very tip top of the parabola, how high up is that, and how many seconds did it take for him to get there? Our graphing calculator has an option underneath the calc menu that'll help us find the coordinates of the vertex. So we select the calc menu and then tab down to where it says maximum. and it'll give us the coordinates of the vertex. There's a separate video in Moodle that shows you how to do this problem using your graphing calculator. When you do that, you'll see that the x-coordinate of the vertex is 0.091. That tells you how many seconds it takes for the spider to reach the top of his little jump. The y-coordinate of the vertex is 80.36. That tells you how many millimeters high he is at the top of his jump. In order to see this parabola in your graphing calculator, you'll need to set your windows in your graphing calculator so that the x-max is 1 and the x-min is -1, and the y-max is 80 and the y-min is -80. That'll give you a view similar to what I've shown on the screen here. A second way to solve a problem like this, and we can do this without our graphing calculator, is to think for a minute that what we're really looking for is the coordinates of the vertex. The vertex represents the point when the spider is at the maximum height in his jump. So if I could find the x and y coordinates for the vertex, I would know some information about the highest point in the spider's jump. I remember that the vertex of a parabola has an x-coordinate of -b/2a. So if I look at the equation above, b is 820 and a is -4500. So -b/2a is -820 over 2 times -4500. When I simplify this, I get -820 over -9000, which gives me 0.091. This is the x-coordinate of my vertex, and since in this problem x stands for the number of seconds since the spider jumped, it tells us that the vertex happens 0.091 seconds after he's jumped. Now I take that x-coordinate and I plug it back into the original equation. So I replace x in my equation with 0.091. And now it's simple arithmetic. I have -4500 times 0.091 squared plus 820 times 0.091 plus 43. When I do that arithmetic, I get a y-coordinate of 80.36. In this problem, y stands for the spider's height. So the maximum height that he reaches is 80.36 millimeters.